Learning target 24 says I can determine the probability a data point will lie within a range of values using the 68, 95, 99.7 rule. So the 68, 95, 99.7 rule, that is that when you have data that is normally distributed, approximately 68% of the time your data point will fall within one standard deviation of the mean. 95% of the time your data will fall within two standard deviations of the mean. About 99.7% of the time your data will fall within three standard deviations of the mean, and then about 0.3% of the time your data will fall outside of three standard deviations from the mean. So in these problems, you'll have information about some situation where data is normally distributed, and you want to use that information to figure out what percentage of the time will your data point lie within a particular range of values. Let's do a couple of problems. So the first one says, one way teachers scale final exams involves setting the mean and standard deviation they would want the exam to have and scaling students' actual scores to get the mean and standard deviation they want. In one of Mrs. Runge's other classes, suppose they scale the final to have a mean of 85 and a standard deviation of 10. Label the following normal distribution and what percentage of students will earn a 75 or higher. So what we want to do first is we want to take this blank normal distribution and label where the mean would fall on this distribution, and then where what values would be one standard deviation away, what values would be two standard deviations away, and what values would be three standard deviations away. And then we'll think about the actual question that's being asked, what percentage of students earn a 75 or higher? So we know that in this problem, the mean score will be an 85 and the standard deviation will be 10. And we know on a normal distribution, this sort of center point happens right at the mean. So our mean will be 85 right here in the middle. And then the values that we're interested in are what scores would be one standard deviation above and below, what scores would be two standard deviations above and below, and what scores would be three standard deviations above and below. So all we're going to do is just add our standard deviation on to our mean. So one standard deviation above would be a 95. The next standard deviation above would be 105. And the next standard deviation above would be 115. One standard deviation below would be 75. Two standard deviations below would be 65. And three standard deviations below would be 55. Now we want to know what percentage of students will earn a 75 or higher. So what we want to know is what percentage of students are going to fall within this portion of the normal curve. Right here. Now when we first discussed this topic, we sort of developed this little diagram where we broke down what percentage of the time your data point will fall within each of these little chunks of our normal curve. And this picture came from this 68, 95, 99.7 rule that I reminded you about earlier. So what we can do now is think about sort of what percentage of the time our data point will fall within each portion of the normal curve that we just labeled. So if we look at this part here, that's between the mean and one standard deviation below. So on this diagram, that's referring to this section of our distribution, and 34% of the time our data point will fall within that particular section. Now, often what people will do is sort of do the same sort of thing for each little section of the graph and add them all up, which is fine, but in this case there's actually sort of an easier way of doing it, which is to notice that the normal distribution is perfectly symmetrical, so therefore if you're looking at an entire like half of the normal distribution, that entire half all added up will be 50%. So rather than sitting there and adding up 34 and 13.5 and 2.35 and 0.15, you can just sort of recognize that the normal distribution is perfectly symmetrical. So this part of the curve makes up 50%. So in total, the percentage of the time that a student's score would fall somewhere higher than a 75, there's 34% between 75 and 85, and then 50% that's higher than 85. So our total is 34% plus 50% gives us 84%. So 84% of students' scores will be a 75 or higher. So in this next problem, it says, suppose LHS students are asked to rate how much they love math on a scale of 1 to 100. Students' responses are approximately normally distributed with a mean of 80 and a standard deviation of 8. And we are supposed to label the following normal distribution, then find the percentage of students who give a rating between 64 and 96. So in this problem, our mean math rating is going to be an 80. And if we label the rest of our normal curve with all of these values, remember we're just going to go up by 1 standard deviation, then 2, then 3, and same thing in the other direction. So if the standard deviation is 8, when we go up by 1 standard deviation, we get an 88. When we go up by another standard deviation, we get a 96. When we go up by another standard distribution, we are at 104. And then we can do the same thing in the other direction. Going down by 8, we get 72. Going down by another 8, we get 64. And going down by another 8, we get 56. Now, in this problem, it's asking you to find the percentage of students who give a rating between 64 and 96. So on our graph, that's going to be here in this region. And so the question is, what percentage of the time when you ask a student are they going to give math a rating between a 64 and a 96? So for this one, you can sort of directly use this quote-unquote 68, 95, 99.7 rule. And remember, that says 68% of the time your data will fall within 1 standard deviation. 95% of the time, your data will fall within 2 standard deviations. So since we're asking about the percentage of students who give a rating between 64 and 96, those are the values that are 2 standard deviations below and 2 standard deviations above. So therefore, we know that 95% of the time, our data will fall between those 2 data points, between those 2 values. Now, if you notice, in each of these problems, typically the situation we're talking about is just approximately normally distributed and not really exactly normally distributed, and so there is some approximation happening here. Like, for example, in our problem context, students had to rate math on a scale of 1 to 100, but if you look at our graph, there's, it's implying that there's some chance that students are giving a rating that's higher than 100, right? Because this very small percentage of the time, our data point could fall higher than 3 standard deviations above, so that would imply higher than 104. There's some small chance that our students could give a rating higher than 104. So as you can see, some of this is an approximation where we're using the normal distribution to approximate real situations. So there is, some approximation going on here, and we're not implying that these situations are exactly normally distributed, but sort of approximately so, and that allows us to answer some interesting questions about the situation, even if they are approximations.